Welcome to Data Science 1, Probability, Central Limit Theorem, Part 2. Things we're going to need to know is the normal distribution, independent, identically distributed, sample mean, properties of the sample mean. IID, what did that mean from before? Let's see. It meant that everything came from the same population. The random variables were the same in the sense that they gave the same probability distribution. So we weren't going from an exponential to a Poisson to a negative binomial. All of the random variables were identical. And the distributions were the same, meaning the parameter is the same across all of them. And they're independent, so one does not affect the other. All right, so we found out that the expected value of x bar is equal to the mean mu of the population, by the way. And we can measure the variability around the mean using the variance of x bar, which is sigma squared over n. Now, from last time, it looked like the histogram of the sample mean across samples becomes approximately normal with mean mu and variance sigma squared over n. But the underlying distribution doesn't need to be normal. The only thing we need is for n to be large enough for mu and sigma squared to exist. And our question we left off with is, does this work for discrete distributions? So we're going to swap things out here, and we're just going to change one thing. We're going to change our uniform to Bernoulli, at Bernoulli 0.5. And we're going to run the simulations like we did before, 1,000 simulations under various n. So this is what it looks like without anything else put on it. And it's exactly what we would think it would be. If there's 1,000 simulations and we have Bernoulli is 0.5, well, Bernoulli can only be 0 or 1. So the 0.5 comes out half the time it should be 0 and half the time it should be 1, or approximately. Now, simulation is going to vary off of it a little bit because it's done randomly. Here I've put in the theoretical mean at a half. Here is the sample means, and you can see that it's slightly off of our true theoretical mean. And here's the normal distribution that's supposed to fit this thing. And you can see it does absolutely horribly. And you wouldn't expect this to be normally distributed because there's this huge gap in the middle. But what we want to do is start seeing what happens as we increase n. So when I go to 2, this is what the picture looks like. And this actually makes sense because there's only two outcomes here. So, and they're Bernoulli, so they could be 0, 0, which would give me an average of 0, 1, 1, which would give me an average of 1, or 1, 0, which would give me an average of 2. An average of 0.5. Again, then here you see 1/3 would show up, 2/3 would show up, and you keep going, and it starts to fill itself in slowly. At 5, you can see we've getting a little bit more. Notice this. Zeros are coming way down and ones are coming way down. At 10, it looks like it's a normal distribution, but it's really not because there's lots of gaps in this. I'm just showing you the picture so you can get a sense of exactly what's going on here, but this is not a normal distribution, as you'll see in the next slide. So if we went to 50, you can see, well, it's kind of approximately normal. We've moved in with the sigma squared over the n issue, right? And because it's pulling it in, that's pulling it towards its theoretical mean. And at 100, this is what the distribution looks like. And you can say it's about approximately normal. It's not perfectly normal by any stretch of the imagination, but it's getting close. So, does it work for discrete distributions? Yes, it does work for discrete distributions. And this works for almost any distribution, so long as it has a mean and a variance. If it doesn't have a mean or a variance, this isn't going to work. So the central limit theorem says if we have some random variables x1 through xn that are IID that follows some probability distribution that has a mean and a variance, then as n goes to infinity, so as the sample size increases, the distribution of x bar becomes approximately normal with mean mu and variance sigma squared divided by n. Okay. There's actually a mathematical proof for this. It's really complicated, requires characteristic functions and lots of other little issues, Taylor series approximations that we don't have enough probability learned up at this point to be able to pull this off. So we're just going to omit it. But it does exist, just to let you know that somebody just didn't do this by eyeballing it. There's a mathematical proof behind it that says this is absolutely true. But this also means that if we did the standard normal transformation, that this thing becomes standard normal. And you will notice that as we go along through this course, things keep showing up that look like this, especially like hypothesis tests. So this is our sort of big result that we're really after so that we can get a bridge between the data and probability, because that's really where we want to be constantly bridging this idea of probability and our data. So in the next video, we're going to start looking at a few ideas that have to do with inference, a little more that bridge our probability with our data, but we'll worry about that in the next video. So see you there.